Hello everyone, good to see you again. I hope all you are doing very well. In this video, I'm going to talk about machine learning, big data, and artificial intelligence. Before you start, don't forget to check out our course website for if there are readings and videos required for this lecture. In this lecture, I first introduce basic concepts of machine learning. Machine learning is a very broad concept of statistical techniques. So understanding what it is, how it works, and when we use it requires mathematical foundations. But don't worry, I'm going to deliver the basic concepts, minimizing mathematical expressions. Those concepts will be delivered with marketing examples. Machine learning is a suitable solution to handle big data. The term big data does not stand for just a large size of data. Beyond the size, big data have favorable properties that provide new opportunities we've never experienced. Google Follow Trend is one of the famous attempts of using big data, but it was finally failed, giving us an important lesson on how to use the big data. I briefly introduced what was going on for your better understanding about big data. Next, another important concept is AI. It is a broader concept than machine learning and was suggested a long time ago. Recent advances in computational methods, which is called deep learning, AI is now widely used in real life. I will briefly introduce what we can do with deep learning algorithm, especially for marketing. All right. Are you ready? Then let's get started. Conceptually, machine learning includes all we've learned in this course. Any systematic, replicable process to understand data and extract valuable information from data is a machine learning method. Machine learning can be defined as a study of methods or algorithms designed to learn the underlying patterns in the data and make predictions based on these patterns. The key point is that the purpose of machine learning is prediction, and it is what differentiates machine learning from traditional statistical methods. Traditionally, econometric methods have been widely used for data analysis. An example is OLS estimator for linear regression. Those methods focus on causal inference about an effect. For example, managers are interested in knowing if increasing advertising expenditure really causes an increase in demand. Econometric methods and applications have been studied to find unbiased empirical evidence for the proof of the causality. Machine learning methods are philosophically a little bit different, focusing on the predictions. For example, consider a decision-making problem of banner ad choice. It is not necessary to show that a banner ad really drives clicks and sales to select one of ad options. Instead, managers want to know which one will generate more clicks and sales. Most broadly, there are two types of machine learning methods. One is supervised learning. Supervised learning is close to precisely the same as what we've learned. There are predictor or dependent variables and a target or dependent variable. The goal of supervised machine learning is to predict the value of the target variable given the predictors. Conceptually, supervised learning is very similar to a class in a school. Researchers give the machine some data as examples, which is called training sample. That's why this is called supervised learning. The machine learns from the examples and then takes a test with other data, which is called test sample. From the test, the machine is evaluated in prediction performance. Examples of supervised learning is decision trees, neural networks, and regression analysis. We will revisit regression from supervised learning perspective. The other is unsupervised learning. Unsupervised learning does not distinguish between variables in data. The goal is to look for patterns, groupings, or other ways to characterize the data. In marketing, we've already used various unsupervised learning methods, including cluster analysis, factor or principal component analysis, EM algorithms, and topic modeling for text analysis. All right, now let's dive into supervised learning with the linear regression. Suppose that we are looking at weekly sales data, and with consideration of price effect and in-store promotion effect, as in this regression equation. This equation is a simple log-log demand model. Log sales is modeled as a linear function of log price and in-store promotion dummy. A machine first learns from training sample. In this regression, we want to know alpha, beta, and gamma. Let's say A, B, and C are our best guess on those coefficients. One solution we have is OLS estimator. This is an unbiased estimator, implying that if the model is true, expectations of OLS estimators of A, B, and C are the true value of alpha, beta, and gamma. This is a desirable property of econometric methods. But supervised machine learning's approach is different from the OLS estimator. Supervised machine learning draws predictions given A, B, and C values per test sample and find the best values of A, B, and C to minimize prediction error. The prediction errors can be decomposed into three different components. First, inherent errors in data, epsilon. This error is irrelevant to the predictors and the target variable, so prediction errors coming from epsilon is irreducible beyond our control. Second, bias. This is a systematically expected or average deviation of our guess on the coefficient from the truth. That is, it is coming from difference between A and alpha, B and beta, and C and gamma. Third, variance. This is also coming from our guess, but different from the bias. It is about uncertainty of our guess. Now, I'm going to give a stylized example for your better understanding on the bias and variance. Suppose that the regression is true and an in-store promotion increases sales but small, like 10 units per week. And there are 100 observations with the in-store promotions in the training sample. Mostly just marginal increases in sales were observed. But suppose that there was one observation with a huge, like 1,000 units, irregular sales increase with the promotion. And suppose that we have two machines. They don't know what truth is, so they don't know that the irregular observation is a false signal. The first machine, Anna, says, it's an outlier, just a weird observation, mostly marginal, so let's simplify it. No in-store promotion effect. That is, Anna's guess on gamma, C value, is 0. The second machine, Elsa, has a different opinion. She stops Anna and says, Anna, wait, what if it's true? We have to keep some units for the in-store promotions just in case. How about 100, 200? or fiber trap? That is, Elsa's guess on gamma, the C value is quite big. Now let's evaluate those ladies' predictions. First, Anna's prediction scheme. It is a simplified or restricted scheme. The truth is that the in-store promotion effect is small but present. So her prediction will be, on average, smaller than actual sales. This deviation is systematically expected because of her biased lens, which is simply ignoring the promotion effect. Second, Elsa's prediction scheme. Her scheme is more detailed and complex. The truth is that in-store promotion effect is present, but small. So her prediction will be, on average, too much. This error was due to sticking on all possibilities that she observed. Elsa predicted in doubt. That is, her prediction has high variance. The difference between Anna and Elsa is called bias-variance tradeoff. Anna has simplified the model. That is, complexity of the model is low. So her prediction is biased, but it's wrong for sure. That is, most prediction error is coming from the bias. While Elsa has made the model complicated. Her model is relatively complex. Her model does not have bias. She found anyway the effect correctly. But the problem she faced is her prediction is uncertain. Sometimes the error coming from high variance is greater than error caused by high bias. What about Anna and Elsa's prediction schemes? First, in training sample, Elsa considered much more of information in data than Anna. Elsa tried to explain all possibilities observed in the data. But for the test sample, because the true in-store promotion effect is small, Anna's prediction error is highly likely to be smaller than Elsa's prediction. Then, although Anna's prediction always incurs a cost of bias, her performance would be better than Elsa. And this problem faced by Elsa is called overfitting problem. She looked at the detailed pattern too much. If she observed a very large number of observations, very close to the population, the observed detailed patterns can be generalized. Well, with a finite sample, the detailed pattern could be a local character, not a general trend. Overfitting problem is a problem of a machine like Elsa trying to fit the model to all detailed patterns. Machine learning solution is to find the best in between Anna and Elsa. This is called regularization. Suppose that there is another machine, Christoph. He suggests, hey sisters, why don't we consider the promotion effect when it seems high enough to be sure? I mean, when we observe significant increases with the promotions several times, his strategy can be implemented by imposing a regularizing function that penalizes substantial variance. So, most popular supervised learning methods for regression, including Ritchie regression and lasso, are based on the regularization. So far, I briefly introduced supervised learning with regression. Then, what about unsupervised learning? As I mentioned, marketing has long applied unsupervised learning methods to various research problems. For example, Marketers employ cluster analysis for classification and segmentation, and vector analysis for customer satisfaction survey analysis, and multidimensional scaling to draw a perceptual map for positioning. And nowadays, they use topping models to quantify unstructured text data. Then, what about aggregate demand prediction? Of course, marketers use unsupervised learning for research questions related to demand prediction, the trend analysis. Trend spotting is kind of market sensing activities. With set advances in online communication, marketers now face tons of data where they can catch up or expect what is and what will be the mainstream of consumer need, want, and demand. There are two types of trend spotting, qualitative versus quantitative way. Qualitative trend spotting is combining through everyday life to discover path-breaking shift in consumer interests, which may lead to revolutionary reshaping of the marketplace. Whereas quantitative trend spotting is relying on social media to track the trend lines of longitudinal measures, which allows for uncovering what's actually going on in the marketplace. Rax-Du and Wagner Kamakura proposed an unsupervised machine learning method for quantitative trend spotting. They use dynamic vector analysis to extract latent common trends of observed time-series data. They propose an extension of the standard DFA model to distinguish seasonal factors from non-seasonal factors. They applied the analysis method to Google Trends data of vehicle search queries. Dynamic vector model is basically a system of equations that share one or several explanatory variables with each other. For example, suppose that there are three indicators, y1 through y3, with one common factor, f. That is, those indicators come from the common factor, so they may have different intercepts, B1, B2, and B3, and different errors, epsilon 1, epsilon 2, and epsilon 3. But each of them has an additive term of the common factor with the indicator-specific multiplier, L1, L2, and L3. Those multipliers are called vector loadings. And this figure presents the Google Trends time series data for some automotive brands. Can you find common trends? I found in Hummer, Jaguar, and Isuzu a strong downward trend over time. Maybe it is a common trend, and there could be some more. The model found several common factors, and this figure displays some of those factors. Black curve is the trend of the factor extracted from all data points, and gray curve is the trend predicted 6 months before each time point. There are some differences between two curves, but overall, trend prediction looks working very well. For validation purposes, the authors measure fitting and predictive performance for the Google search queries. As you can see, the fitting performance looks good, but predictive performance looks poor for some names. But the predictions look catching up the trend. One of the valuable information we can get from this analysis is the information about potential antecedents of the common trends. The authors related trends to some economic indicators, including unemployment rate and gas prices. And the results show some possibility to predict the search trend from economic indicators. All right. Now, let's move on to the next agenda, big data. The term big data implies not only big volume of data. IBM's definition is widely used to conceptualize big data, 3 V's, 4 V's, or 5 V's. Some articles introduce only the first 3 V's, volume, velocity, and variety. Others introduce the fourth one, veracity, and sometimes the fifth one, value, as well. But the first 3 V's are the key to characterizing big data. First, volume. Big data definitely indicates larger amounts of data generated from a range of sources. But not only the volume, but also the others. Second, variety. In big data, there are multiple kinds of data that involve a situation or event to be investigated. For example, social media generates structured user log data plus unstructured text, pictures, audio, and video. Third, velocity. A tons of data is generated a day, an hour, a minute, and a second, and the data generation is getting faster and faster and faster. In line with the data generation, we also need to speed up decision-making. For example, YouTube's recommendation system works in real time to reflect so many video clips newly generated every second. To handle big data in real time, computing speed is also very important. Computer scientists developed solutions based on MapReduce concept. Suppose that there is a computational task with big data, and let's hold the task on application. MapReduce breaks the application into several subproblems. First, MapReduce is doing map, which means assigning the subproblems to nodes of computers. Then it is doing reduce, which means combining the results from the subproblems. This MapReduce concept allows for distributed or parallel computing to handle 3 V's of big data. Most popular solution is Hadoop, which is an open source version of MapReduce. So, big data allow us to access a large number of data from new perspectives in real time. Then, how to extract valuable information from big data? Google Flow Trends might be the first famous attempt. People ask Google when they need information, especially when being sick. So many people ask Google first instead of visiting doctors because my doctor is so far from me, but Google is always next to me. Flu is one of that kind of sickness. So Google brought up a hypothesis. If an influenza epidemic is coming, an increasing number of people may show health-seeking behavior in the form of queries to online search engines. So, Google collected weekly count for Google search queries over 5 years from 2003 to 2008 and developed a model to track influenza-like illness in a population. This figure displays the fitting and prediction performance. Black curve is Google's estimate of influenza-like illness percentage for the Mid-Atlantic region, and red curve is CDC reported influenza-like illness percentage. We can find that the performance pretty good enough to use in reality. Especially, the prediction performance was amazing. Correlation between the predicted and CDC reported values was 0.96. However, Google flu trend finally failed. This science article explains the failure of Google flu trends. The authors introduce big data hubris. People often assume that big data are a substitute for rather than a supplement to traditional data collection and analysis. That is, the foundational issues of measurement, validity, reliability, and dependencies among data are still alive in analysis with big data. From the late of 2011, a systematic discrepancy between predictions and CDC reported values appeared. Combining Google flu trends with other traditional data, like lagged CDC data, significantly reduces the discrepancy. Why this happened? The authors introduced a concept of algorithmic dynamics. Algorithm dynamics are the changes made by engineers to improve the commercial service and by consumers in using that service. Several changes in Google's search algorithm and user behavior likely affected Google flu trend tracking. The Google search algorithm is not a static entity. The company is constantly testing and improving search, and the changes affected search behavior. For example, Google reported in June 2011 that it had modified its search results to provide additional suggested search terms and reported again in February 2012 that it was now returning potential diagnosis for searches including physical symptoms like fevers and cough. The former recommends searching for 3 months of the flu in response to general flu inquiries, but the latter explains the increase in some searches to distinguish the flu from the common cold. Here, I want to quote the key point of the article. Google flu trends bakes in assumption that relative search volume for certain terms is statically related to external events, but search behavior is not just exogenously determined, it is also endogenously cultivated by the service provider. This is what Google flu trend missed. This example implies that big data is a really good game-changing weapon, but it does not change the rule of war. Now, I'm going to briefly talk about the third topic, artificial intelligence. As well as AI and machine learning, you may hear deep learning from lots of people and media. What's the difference among them? AI is a conceptual term. It includes any effort to automate intellectual tasks which are normally performed by humans. An example is interactive voice response. When you call a company, now a machine with human voice is welcoming you. It guides you to the service that you need or the best representative person who can solve your problem. Of course, it is not perfect. Sometimes I just want to directly talk with the representative person, but anyway, it is the most popular AI in real life. Machine learning is a part of AI. It is an algorithm, or a set of algorithms, to search for useful representations and rules of data. We already discussed what machine learning is in details in the first part of this lecture. Deep learning is a way of machine learning. It has multiple layers to learn data representations and the number of layers can be very large. That's why it is called deep learning. It has received attention because it allows for automating many tasks that we've failed to automate. This is a short list of what we can do with deep learning now. AIs with deep learning now easily beat humans at professional board games, Go, and chess. And in many tasks, including image classification, speech transcription, handwriting transcription, and autonomous driving, AIs show near human level performance. Those developments now allow for natural language process like translation, text-to-speech conversation, and answering natural language questions, leading to release of digital assistants such as Amazon Alexa. In marketing, AI technology based on deep learning algorithms has widely used for ad targeting and recommendation systems. All right, that's all I have in this lecture and in this course. After watching this lecture, please check out our website again for if there are additional readings and videos required or strongly recommended, online quiz assignment, and hands-on exercise in our software. And thank you. Bye.